All right, so today I'm going to be talking about the new features in GoldSim 15 that were just that we just released earlier this month, and I'm pretty excited about them. Some of them are more minor than others. I'll go through each of them and also share with you a couple of examples demonstrating how they could be used. Okay, so like I said, if you have any questions, let me know during the presentation. I might answer them at the end. So the first one I wanted to mention is our online help documentation. It's all online now. I mean, it has been for a while. We just upgraded it to HTML5, just making it easier for us to publish it in a modern framework, and just kind of keeping everything up to date. So yeah, like I said, and there are some other things too that I don't even have on this list that have to do with the graphics. Monitors have really become a lot more like high resolution. So we needed to make a lot of changes to accommodate a higher resolution screen, for example. A lot of these things you don't really see that much, but they are important overall with how it looks and how it operates. So the next one is this feature to allow you to insert elements just by using shortcut keys. So we're always trying to think of how can we make the process just a little bit faster. So this is just for inserting new elements, and we only have a selection of 10 that you can pick from, and they are numbered 0 through 9 on your keyboard. Just hold down Control and hit the number in your graphics pane, and you'll see the elements appear. So for example, Control and then 1 would put down a new container element. The next one is the ability to transform between data and expression. I'll demonstrate that just in a bit. And then we've improved our versioning capabilities. So I don't know if you've used versioning very much, but I'll demonstrate how we've added a little bit more to that just to make it a little bit more detailed and user friendly. And then a big one that I wanted to mention is this new element called the controller, mainly for controlling flows, but it could be controlling various other aspects of a system. All it needs are you need to be able to have something that you're trying to control, which is usually a state variable. If you have that, then you could really use it to control a lot of different kinds of things. But I'll walk through some examples there, and then I'll end with demonstrating how the simulation performance has increased in GoldSim 15. Okay, so that's a summary of all the things. So let's go ahead and start. I'll start with the data and expression element conversions. So let's say we have a data element that is, well, let me start with just a more basic data element. Let's say we have just a scalar data element here, and we've already defined it with, let's say, units of meters. So we have 2 meters here, and what we can do now is you can right-click on the element and select transform to, and if I select expression, then you see everything's the same except for the type of element. Now it's a different kind of element. So this is the only transformation that we allow. So if you're wondering, well, why did we pick this one in particular? And it's really just because this is a common one to change as you're building a model. A lot of times you might think you have data that drives the model, and then later you find out that, oh, wait, it needs to be calculated, or the other way around. And sometimes these things are connected to a lot of places in the model, and it just makes it a lot easier to just do a transformation like that. You might have to end up changing the definition. If it's a simple one like this, it just translates correctly directly over, but there are other situations where it may not, like a vector, for example. So if we have a vector of values like this, it doesn't transform as nicely, even though technically you could build this same vector with a vector constructor expression. We're not going to bend over backwards to try to get exactly everything the same, because there's always going to be something that's different. So if you translate this one, so if I just do that, transform to expression, then what it does is it just wipes out the equation. there. So there are some times where it may not give you exactly what you need, but the important point is that it immediately just creates the same an element, well, a totally different element that can do something different with an entirely new name, or sorry, the exactly the same name that then can be immediately linked automatically to all the places it was already linked before. So that can save some time. Okay. So the next thing is the versioning. Yeah, so the versioning, and let me just open up an example. Let's say we have this model here, and versioning has been used for a long time, as you know. And in this model, it's been incremented many times, so it's gone through many changes. And this is really useful when you're working as a team with others, where you're passing the model back and forth, and you want to make sure that everybody's aware of the changes that you've made. The nice thing with the new version now is we can do two types of reports. We can do a version report, which will essentially summarize all the different versions that you've created. So in this case, we've got more than 10 showing up in here. It would list all of these by name with their description and their version number. It wouldn't say anything about the individual changes inside of each one. That's what a change report is for. And it also depends on which of these versions you have checked. So if you're only looking at this current version, then the version report would only, if I click on this, you can see it only reports on the current version. But if I were to instead skip down to here and check this one, then if I click on version report, you'll see that it shows the summary of all of the versions up until that point that I've checked the box. And then if you go to changes report, it shows it drills into each of these different versions and tells you, essentially the main basics of what's changed. It doesn't tell you every single thing. It tells you if the element has changed, if it's been added, if it's been removed, that kind of thing. And that's how versioning has always been in GoldSim. But the added benefit here is that we have an ability to report on things differently, but then also, which is this other thing that's really nice, is when you create a new version. So let's say let me make a change first. Let's say I make a change to this model. I say I don't need this, and I remove this. And then I go up here and I say, okay, now I want to save a new version. So I'll create a new version and give it a name and a description. And then when I click OK, it'll say, okay, now we can save for archiving. We can save a copy of that version, and it will append the name or the number of that version. So this is the 1.028. That's what it already had. So that automatically gets appended, and then you can save that and then move forward to the next, whatever you're doing next after that. So it's a good way to say, for example, you want to make a bunch of changes and then send it off to others to review or start from where you left off. Then you could do it this way and save the file when you're done making the changes, and then send that over to whoever else is working on it, so that the file name always has the version number associated with it. Although you can always opt out of that as well. Okay, so that's the versioning. And then the next thing I want to talk about is the controller element. So I'm going to start with a very simple example, and this is just a tank. So imagine you have a tank up on a hill, and then you have some sort of unlimited water source, and you're pumping from that up to fill this tank and keep it full. But in the meantime, the tank is discharging water at a rate to feed some sort of demand somewhere. And in our model, I'm using the word feedback here in both of these cases. Likely that is something like this is happening in the real world, but it's important to think in terms of flows and feedback when you're working with a controller element. This is what the controller element looks like, and I'll talk about it in a little bit, but first I want to just present this concept because it is important to think this way when you're adding them. So in our system, we have this, I'm just calling it some industry that requires some water from this tank. And so the only way to really control that or simulate that is to try to represent that kind of that feedback process where the industry says, okay, I need some water, so I'm going to ask for it. And that's probably done in a way of like automated, opening a gate or opening a valve or something, or turning a pump on or something. But that happens and it tries to draw water out of this tank. And at the same time, we're trying to fill the tank with this other system over here. So what this model will do is it will simulate that whole process. And so that means we need to be keeping track of how much water is in the tank at all times. And so we do that in here with this pool element. The pool element has, an inflow that's coming in. That's our controlled pumped inflow. And then we have an outflow, which is that water demand. So that's what's pulling in and out of this pool element. All the while, we are keeping track of its water level so that we can provide feedback to say whether we need to increase the flow from the pump or decrease it, depending on where we sit in regards to some sort of target water level or target volume in this tank. Okay, so those are kind of the ingredients that we need in order to be able to use this controller element. So if I go into this container, and this is just an image I just put in there. I created this image in PowerPoint and then replaced the container icon with this. Anyway, so we go in here and what we have here is a target. So I have this in meters, 3.5 meters. That's where we want the tank to be, if possible, at all times. And so what we need to do then is we need to look at how far we are away from that target, and that will drive whether we turn the pump on or turn it off. And in this case, we're using a deadband approach. You can also you can use other approaches. The deadband approach is an on-off scenario where it's a constant flow, and in reality, a pump would not be quite constant because of its operating curve. But essentially, we can say, well, for simulation purposes, with a one-day time step, constant flow is good enough. And so with a deadband approach, you're talking about an operating band. And when you're in between the top and the bottom of this band, you don't change operations. You just stay in whatever pattern you were in before. And then as soon as you hit the top or the bottom, depending on whether this is controlling inflow or outflow, you're going to have it turn on or off. And so that's what the status element is intended to do. And I've presented this whole concept using the status element many times in webinars previous to this. But I'm just telling you, this is the basics of what the new controller element will take care of, because this is when you start dealing with a lot of tanks and ponds and reservoirs in your model, this can just add up, dealing with all of this. So essentially then we just say, okay, what's the flow capacity when it's turned on? And then otherwise it's turned off. And then you just use a selector element. You say, when the pump is on, then you're going to pump this maximum flow. And then you just link this up to your tank. In this case, we say, okay, the flow is moving this direction. So I just colored this link. And if you double click on the link, you can see where it's coming from. It's coming from our pump calculation, our controller essentially. And it's going right into our tank. And then the feedback is essentially monitoring the volume. In this case, we're monitoring volume, but in reality, you might be monitoring the level, but that can easily be back calculated. But the point is that as soon as we hit the upper and lower parts of the deadband, then we will turn the pump on or off, depending on which we were doing. So, and then we can also run the model and look at that, but I need to first delete that. Okay. So then we can run the model and kind of visualize how it's operating. And in this case, what we're seeing here is the target in this kind of gray solid line, and it's dynamic. The target moves. So right after day, I think it's around 65, we jump up in the level, and our operations need to respond accordingly. And so that's what this is doing. The red line is the volume in the tank. And you can see here that at the beginning of the simulation, we were above the top of the deadband. The tank was. So the pump was not turned on because there was too much water in the tank. And then it didn't do anything. There was no response until the tank level hits the bottom of the deadband, at which point we turn the pump on and it stays on because the tank now level is now low, and it won't turn off until we get up to the top of the deadband. So the whole purpose of this is to prevent rapid oscillation, and so that's what the deadband is doing here. So now what we can do is now we can simply put in a controller element. So the controller is in the functions category. We put this in here, and then I'll define the flow and quantity units. And now we just need to link to a process variable. And the process variable is whatever thing we're monitoring or whatever thing we're trying to control. In this case, the tank volume. So I connected that. And in our case, we're trying to control the inflow. So I'm going to change this from the default outflow to inflow. So that's the flow direction. That's what we're trying to control, something that's flowing into the tank. And then the flow capacity, I think I already specified that inside of that pump. Let's see, flow capacity, there it is. Then deadband, and then our deadband is defined using both a target and a top and a bottom. So I'll just say top and bottom since those are already defined. So deadband, okay. Oops, I accidentally hit cancel and I have to start over. But let me just build that really quick inside of here. I think it'd be better just to build it in here. This is where all the data is. Okay, liters per second, cubic meters, tank volume, flow capacity, deadband top, deadband bottom. Okay, so there's the controller, and that's going to essentially replace this thing called discharge rate right here. So I'm going to go into the tank and just replace that. So the pumped inflow, instead of being that discharge rate expression element or status element, or I mean selector, I'll just connect to the controller. And then we'll go back over to the pump, and we can see here that this is not being used. Now this is being used. You can see it's got the indicator in the output port showing that this output is being used by the other element. This one's no longer being used. This one's not being used. So that's what we've replaced right there. And so now we can run the model, and I think there must be an output that's missing. Oh yeah. But anyway, oh yeah, now, yeah, the output's missing. So let me change that. So I'm connecting to the controller output. In the real world, what you'd probably rather connect to, however, would probably be the actual outflow. They're probably one and the same. In this case, they would be. But it'd be safer to, if you're trying to report on what, sorry, this would be the inflow actually to the pond. So the total inflow. If it was an outflow, you'd want to connect to the outflow of the tank. But anyway, the controller output and the inflow to this tank should be one and the same in this case. And okay, so my inflow is okay. I need to think about this for a second. Okay, this is not what I expected. So let me look at this again. So I have the water volume connected here is 100 liters. Okay, and it's never turning off. So I think, let me look at this one more time. The pool is overflowing. Okay, I need to connect to the outflow from the pond. Total outflow. Okay, and our pumped inflow is here. Oh, so our I know what I did wrong. I forgot to change the flow direction at the controller. Okay, so we are controlling inflow. So that's why it thought it didn't ever need to turn off because it thought the flow was going the other direction. Okay, so that's what I forgot to do. Yeah, the flow direction is an inflow. So let me go back over here. Okay, there we go. So now it's operating the same way it was before, where it's trying to keep the water level in between the top of the dead band and the bottom of the dead band. Okay. Yeah, okay. Someone just notified me of that. Thank you for that comment. Yep. Okay, so that's kind of how that's how this controller works. Now what can we do with it? What are some other things we can do? Let me first show you an example where we've got all three of the different types of controllers that you can use. This is a model that we have up on our online library. That allows you to assign a different type of controller for each scenario that we're looking at. So in this case, we have three scenarios. We have one that uses a deadband controller, another one that's a proportional controller, and also the PID controller. So those are the three different types of control mechanisms you can choose. So if you go to the controller element, you'll see we were looking at deadband before, but there's these other two. And so what this model does is it has all three types, and then depending on the scenario, it just will pick whatever one we select and use that outflow. Or sorry, inflow. Again, in this case, it's inflow. We can run all the scenarios and see how they compare. And this chart down here at the bottom shows the difference in the water levels. So the one that's the obvious different one is the deadband type, because that's an on-off type of controller. So you'll always see kind of the jagged teeth kind of look with the deadband controller. That's just the response that you'll get with on-off. And then the proportional controller is just a linear proportion. So you just have a proportional gain constant that all you do is multiply that essentially by the error that you are away from the target. And then it just applies that value. So the further you drop below or go above your target, the more that your controller will respond to that. If you give it a higher gain constant, then it will respond with higher magnitude relative to the error from your target. So with the PID controller, that would be doing also the proportional gain, but then in addition to that, you'll add integral gain and derivative gain to that as well. And the integral gain would be then if, let's say, for example, that you have a target, and let's say we're looking at this chart here. The target is shown in this dark gray solid line. In the case where we have an error, like in this, the red line is above the gray line. That's a positive error. We're above the target. If you are sitting above the target for a long period of time, and then you take that area above that target, the integral of that amount above the target, then that would contribute to your integral part of the equation. And so the higher that you set your integral gain to, the more impact that kind of phenomenon would have on the response. So if you had, let's say, a very small error, but it lasted for a very long time, then that would have a greater impact, and you could have your controller react more to that or be more sensitive to that than a proportional controller only would be. And then similarly, the derivative gain would then would impact you when you have a significant or more significant change to the error. So in the case of this model where we have a sudden drop in our target, then your PID controller, the D part of that, might be able to react better to a change like this. But most of the time, what you would see in most cases, most real world cases, would be the P, and then maybe sometimes the PID, but mostly with just the P and the I part being having a significant impact. In most of the kinds of models you'll see, we think, in GoldSim. Okay, so those are the three different types. And then somebody said, can you see any uses for the controller outside of water management? And I could see the controller being used for things, anything where you would want to be controlling the flow of something moving around. And it doesn't have to be, it could be flows of whatever you might be modeling. And in this case, you're trying to control that. And this is just a kind of conceptual way that you can control it. With a proportional, yeah, you could control the flow of migration of people or money in a financial system, I suppose. Maybe it's also modeling, controlling temperature in a room, for example. You might control the airflow using one of these, or simulating the control conceptually using this. So yeah, you could. Something that someone asked earlier, it was a good question. So I built this little thing, and essentially it's two controllers in series, sort of. This was envisioned earlier, and this was the question. What if we had two ponds, and we're controlling the flow out of the first pond? So this is an outflow controller. So it says outflow. We're controlling the flow outside of this pond, and that water that we control is flowing into this other pond. But at the same time, we don't want to put too much water into this other pond. So it's actually the combination of both these ponds that we're using to control this flow. So that's what this thing does. It's controlling flow out of this pond using two ponds, actually. And the best way to describe it, in addition to, I guess, walking through it, is to show this chart. And what this chart is showing, let me do that. Okay. So what this chart shows here, you kind of have to look at the colors. So the blue is referring to pond 2, the pool 2 over here, and the red is referring to pond 1, and the solid line is the volume. So the solid red line, you see it's starting at 10, and it starts to rise, it starts to go up. And in response to that, this first controller is going to say, oh, okay, it's going up, so let's increase our outflow. So it starts to do that. You see the outflow is going up because our volume is going up. So that would be, what a typical proportional controller would be doing. But then we get to a point where it gets up here, and all of a sudden our flow starts going down. And this is because of the other controller now kind of controlling overall. It wasn't controlling before, and that's because there was plenty of extra storage capacity in pond 2. You can see down here, it's dropped way down. So there's plenty of capacity in pond 2. There's nothing holding us back. And so therefore, we're just going to be looking at pond 1 and just basing everything on that. Then we get to a point where all of a sudden the tables turn and pool 2 becomes more important because it's filling up. So pond 2 gets more full. So it's saying, okay, that's, we don't want any more. So it's going to control more of what's happening, pulling out of pool 2. So how do I do it? So this is how we set it up. So I do the same thing as before with this first controller. Is I point to pool 1. That's the pool I'm looking at, monitoring to control it. And then I do this kind of different thing where I say, okay, I don't want to just pump the capacity of whatever this thing can pump at. I don't want to just go on or off completely. I want to control this flow capacity, and that this capacity is being controlled by the other controller. So essentially, it's like overriding it pretty much. So that's how the overriding happens, and that's how this whole controller in series can work in this type of a case. Okay, we might also have another type of situation where maybe we have a bunch of models in series. And where did I put that one? I guess I don't have it open at the moment. Let me go find it. So in this other case, maybe you have, and it doesn't have to be a canal necessarily, but you might have a series of systems in your model. Maybe there are multiple ponds, but they're all operating kind of in a series. And you might simulate them in like a series of bathtubs, for example. And that's what I'm doing here. I'm assuming we have this really flat area with these long canal systems or long segments of canal, and I'm assuming uniform flow and large enough time steps, and also it's flat enough that we can conceptually model this without any effect of the flow dynamics or energy differences. So it's just mass balance. Anyway, with each of these pools, we can then represent segments of a canal that has, let's say, a gate downstream of each of the segment. And then we can just model these with some sort of incoming flow that we don't have control over. We would have to respond to that. And then we could have each successive pool then respond to whatever's coming into it. And so that kind of thing could be simulated with multiple controllers. And so here's a plot showing the water depth at each. Well, I should probably change this to be auto. Okay, so if we were to zoom in to one little spot here, then what you see here is that we have a little bit of a delayed response, which kind of makes sense. That each one, because each one is responding to whatever's happening upstream, the flow coming into it. So there will be at least one time step delay between one and the next. And it also depends on the constants that you're applying to each one. In this case, the canal gets smaller and smaller as you go downstream. So your coefficients would be a little different for each one. But essentially, you could do it if you're simplifying the model in the way like this. Just by simply putting a control at each pool and controlling them independently of each other. And that's the key really here. But in a lot of cases, they may not be independently controlled, right? Kind of like what we talked about earlier. And so in reality, you might have something else here where you'd be looking at the whole system, or maybe you'd be looking at an average of upstream and downstream levels, things like that get a little bit more complicated. But this is also getting into the area where it would probably be beneficial to do a sensitivity analysis of your controller input parameters. So in this case, we have a controller here. It's a PID, and we're using these three input parameters that I was talking about before. And so what you could do is you could say run a sensitivity analysis to see, what impact does this parameter, the proportional gain constant, what does it have if it's applied to all the segments? What impact does it have on, let's say, for example, the maximum or minimum water level or change in water level? Something like that, for example. So to do that, it would be quite easy. It turns out that I'm already monitoring all the water depths and all the channels right here. So I just used a data element set up with a vector that just references to all the volumes of each of the reaches. And then I convert those volumes into depths. So I have a vector here of all the depths. So then what I could do is I could say, we're trying to calculate the maximum water depth in all, all the channels. So I'll go over here and I'll I'll use the built-in function max vector, all depths. And so this would calculate the greatest of all the segments of all time. What's the greatest water depth? And so now that we have that, it says the greatest value is almost 5.2. The target is 5. We have a target depth of 5 feet. So then what we could do is we could say, let's do a sensitivity analysis that looks at this extrema. And then we could say, what if we adjust this number, Kp, and we adjust it from 0.01 all the way up to 10 with a middle value of 1. And then we can run the model multiple times and see a plot of how it impacts. So here's a plot. And so it's showing us that once that value reaches 1, a value of 1, it really doesn't make any difference what we set that value to in regards to the peak water level that we might see under this control regime. So it's a nice way to essentially conceptualize the operations where you have a lot of operations of a lot of different components in your model, but you can kind of conceptualize them all the same way. I mean, in reality, you might not use the same you might not use these same constants for all the reaches like I'm doing. They might be different for each one, but it's still a parameterized model that is doing a pretty complicated thing with all of these controls. But it's definitely something that I feel would be useful in a lot of your typical water balance type models. Okay, so the last thing I want to talk about is the performance gains in GoldSim 15. So let's go there. So I had to go find an example that I was familiar with. This is the model that I worked on. And I'm going to open it in both GoldSim 15 and GoldSim 14. So let me just do that. I know this might look like there's a lot going on in here. I was just looking for a model that had a fairly long runtime. Okay, so I'll start with the model running in GoldSim 14. And so it runs for a historic period, and then it goes into a future period. Well, at the time this model was built, it was future. It's not anymore, but it has some stochastic elements in it, and it runs for 10 realizations. So it should be around 30 seconds. And so it says 29 seconds. You can see that down here. It took 29 seconds to run this one. So now over here on the left, we're going to GoldSim 15. And 15 seconds. So that's what it's been at. It's about half of the time. So that's a pretty good improvement. And it really, I can't say exactly, if it'll be half for you in your case. It really depends on a lot of different things. This model, it turns out, if I go to the information tab, it shows that it's got, as far as number of outputs, over 5,000 outputs, less than 1,000 elements. So not a huge model, but a pretty big one. So it depends on a lot of different things. But I would imagine that for most of your larger models that you should see at least some improvement to the runtime, which would be really nice. All right, so that concludes the presentation, and I am happy to answer any other questions that you might have or scenarios that you might want to look at. So I'll wait around here for a bit. But otherwise, thank you very much for joining, and hopefully you'll get a chance soon to start using GoldSim 15.